Hello, in this video I'm going to discuss the material that occurs in the second half of Chapter 2 from your text on electron configurations and periodic properties. In particular, we want to be able to predict electron configurations using a series of rules and tools that they supply in this chapter. In other words, the order of filling of the electrons as we proceed from hydrogen through helium and onto the rest of the elements in the periodic table. Most of the filling of electrons in the elements are pretty straightforward, and you've done this previously in your general chemistry courses, but in this course, since it's focused on various elements, we're going to look at some of the inconsistencies and hopefully using the tools in this chapter be able to explain those slight variations in the trends that occur. So for instance, nitrogen has a slightly lower ionization energy for its first electron than oxygen, and using the information in this chapter you can explain why that occurs. So this diagram from your book shows the relative energies of the various electron energy levels, starting at the principal quantum number 1 up through 5. So n equals 1 up through 5. Notice that on the left-hand side, the energy is only determined by the principal quantum number n, and that is for hydrogen-like type of atom, so anything with just one electron. And the reason for this is because there's no electron-electron interactions in a one-electron system, of course. Once you start adding in those electron-electron repulsions, sometimes known as shielding, in a multi-electron system, then the L quantum number starts to become important. And you can see that we have then a splitting of the orbitals for any given particular principal quantum number. So for hydrogen-like atom, at the n equals 2 level, there's no difference between an s and a p orbital. But in a multi-electron system where we have electron-electron interactions, those split. And you want to pay close attention to the fact that the splitting of those orbitals is fairly large, but not large in comparison to the separation of the principal energy levels. However, as you go higher and higher in the principal quantum number, those energy levels start to mix, and that's what causes some of the inconsistencies in the periodic properties that you've observed previously in your general chemistry courses. The periodic table is probably the easiest way to determine the electron configurations, the order for filling, for the simple, straightforward cases. This periodic table is color-coded according to the orbitals that are filled for any given place in the periodic table. You've seen this before. So for instance, hydrogen, right, you're filling in an electron into the 1s orbital, and helium, you fill that orbital, and then on the second row you start filling in the 2s electrons followed by the 2p and so forth. These energies on the periodic table follow the same order of energies that are shown in this diagram right here, which of course shows that the 4s orbital is going to fill before the 3d, which is what happens, of course, if we follow along in the periodic table. So an example of a simple case, beryllium. I've drawn out the orbitals in the format that you're used to seeing from general chemistry, but of course this follows the same trend as shown over here. When we fill in the electrons, you want to be cognizant of the rules that you learned in general chemistry, Aufbau, Hund's rule, and Pauli exclusion principle, and they're going to be used similarly to help us determine the order of filling. So first electron goes into the 1s orbital for beryllium, and of course, since the energy gap between the 1s and the 2s is large, our second electron, instead of going up into the 2s, is going to go down and be paired in the 1s. Now, there's a consequence to that because the electrons are closer in proximity, and therefore there's some electron-electron repulsion. But since the energy gap between the 1s and the 2s is greater than the electron-electron repulsions, represented by this symbol, the electrons prefer to pair up. And then, of course, we are obeying the off-bow principle, which requires that we put electrons in to provide the lowest energy for total energy for the atom. And, of course, the Pauli exclusion principle, which requires that we have separate or non-identical quantum numbers for all of the electrons in the atom. And then the next electron that we need to fill in to complete our beryllium is the 2s electron, and that goes in like that. When we move on to the next one, that one's going to pair up also because, again, the energy gap between the 2s and the 2p orbitals is large enough that the consequence of the electron-electron repulsions from pairing them in the same orbital is relatively small. Next, boron has one more electron. We have to add in a 2p electron. That goes in. I'm putting these spin up first just because out of habit. There's no particular reason that I have to do that. So this is boron's electron configuration. Carbon, which is the next element across the periodic table, we have to add another electron in. Since the 2p orbitals are degenerate, in other words, they are equal in energy, I can add that electron in at any position, but I want to keep it spin up the same as the first electron I put in. And the reason for that is that there is a slight decrease in the energy or energy lowering, having the electrons to be all the same spin with one set of suborbitals. Okay, and so in this case we're obeying Hund's rule of maximum multiplicity, and again the reason for that is that it keeps the energy of the atom lower. Now, that doesn't mean that you can't have alternate configurations. They are just higher energy, in other words, excited states. So shown on the bottom is the original electron filling that we did for carbon. Here you can see we're just representing those 2p electrons. The lowest energy being spin up. If we were to flip the electron spin of one of the electrons so that they are no longer both of the same spin, there's an increase in energy, which is called the exchange energy. So actually usually refer to extra exchange energy as lowering the energy of the atom, and this is where we get the Hund's rule. This instance in which we have one spin up and one spin down, one positive 1/2 and one negative 1/2 spin, results in an increase in energy due to a loss of exchange energy shown here, pi sub e. If then we further move this electron into the same suborbital as the other electron, there is a further increase in the energy to produce an even higher energy excited state in which those two electrons are paired, and of course that repulsion between the two electrons is represented as pi sub c. These terms, the exchange energy and the energy of repulsion between electrons represented by pi sub c, are going to also become important in explaining some of the inconsistencies in the trends in the periodic table. So for instance, chromium, which you know has an electron configuration, if you look in one of the tables in your text, of 4s1 3d5. In other words, some of the d electrons have filled in before all of the 4s electrons have filled. Notice that in our previous table that the 4s and the 3d energy levels are very close, so there's not a big energy gap between those. And so what we're going to do in class is to use these terms, the terms of the exchange energy and the Coulombic energy of electron or electron repulsion, to explain why chromium has this particular electron configuration rather than 4s2 3d4. And we'll go into more detail and do some further examples within class, within the groups. Two more tools that are presented in your textbook for helping to predict the electron configurations are the Slater's rules and Rich's periodic correlate. There's a diagram in your book. I think it's figure 2.12, which we'll use to help us predict or explain the filling of d electrons within the transition elements. Let's start, though, with Slater's rules. The basic principle is that behind Slater's rules is that shielding, in other words, electron-electron interactions that affect how much of the positive charge of the nucleus is felt by each electron, can be used to predict or understand the order of orbital filling. Particularly, this is helpful for the transition elements and some of the other anomalies. And the idea here is that the effective nuclear charge, which we're calling Z star, is going to be less than the full nuclear charge by some parameter S, which is called the shielding constant. And basically, using Slater's rules, we will calculate S for a given electron in the atom, subtract that from the Z, and get the effective nuclear charge for that electron. And just to sort of pictorially show what this means, if you have a nucleus with 3 positive charges, imagine an inner core of electrons, right, close to the nucleus, and then an outer shell of electrons, right? The electron-electron repulsions between those two is going to weaken, right, the intensity of the positive charge that is felt by that outer electron. So then this is called shielding. So these inner electrons in this shell, due to electron repulsions, shield these electrons and decrease the amount of positive charge that they sort of feel. And that results in the effective positive charge of the nucleus felt by those outer electrons. We can also show this graphically using the radio probability functions that we discussed earlier in the course. And so looking at for instance, the radio probability function for the 1s electron density, you can see it's confined very close to the nucleus. If we overlay that on top of the radio probability function for a 2s electron, or for a 2p electron, you see that the 1s, of course, has a higher probability close to the nucleus, and therefore is going to be able to shield the electron density of a 2s or a 2p electron, which are primarily, which have a higher probability out further away from the nucleus. We can show this again also for instance, the 3p and the 3d, overlaying the electron density of the 3p onto the 3d. You see that the 3p electron has a small probability of being very close into the nucleus, right? This probability here, followed by a node, and then the larger one. This extra probability of being very close to the nucleus helps the 3p to be a little bit less shielded by other electrons than the 3d electrons are. So for instance, if we overlay the electron density for the 2p, right, on top of our 3p and 3d radio probability functions, you see that the extra electron density here for the 3p, right, will allow it to be a little bit less shielded by these 2p electrons than the 3d electron is. So it's slightly more shielded. This results in an ordering of the electron orbitals in Slater's rules as shown here. So the 1s electrons closest in are not shielded by anything except for other 1s electrons. Everything to the right of this, though, the right of the 1s, will be shielded by these 1s electrons. Everything to the right of the 2s and the 2p will be shielded by those electrons. And the further out, usually the greater extent of shielding. So the 3d is separated from the 3s and the 3p, even though they're in the same principal energy level, because the 3d, as we showed down here, is going to be slightly more shielded than the 3s and the 3p electrons are. And then, of course, the rest of the orbitals are ordered in this fashion, using, again, the radial probability functions and some experimental evidence. And there we go. You will use some numerical values for the level of shielding for each particular set of electrons to calculate S and determine then the Z effective. So, for instance, and I'll let you look at the specific examples in your textbook because they're actually very well written and pretty easy to follow, but if you have an electron in the 4d orbital shown here, we can calculate how much an electron in this orbital is shielded by electrons in the same orbital, right, by assigning a certain numerical value, how much it's shielded by the electrons to the left in the 4s and the 4p level, how much shielded by the electrons in the 3d, and then so forth. Adding all those up gives us S. We subtract from the charge of the nucleus to give the effective nuclear charge. Again, go over those examples in your textbook because they have several that are very nicely written and I think pretty easy to follow once you understand sort of how this works. And then finally, I'm not going to go over specific examples using the trends in the subshell energies for transition metals that are shown by this paper by Rich, but I do want to just discuss this diagram so you know how to use it for when you get to class and we work on the specific problems. Basically what this is showing, and we'll start with the top diagram, you can use the top diagram and the lower diagram separately. This is for neutral transition metals, and this part of the diagram are energies for the orbitals for +1 metals. And you can see there's a slight shift when you go from a neutral transition element to one with a positive charge. Basically what you're looking at here is these two lower lines represent the energy of the electrons in the s orbitals for these transition elements, and these two parallel lines represent the energies for the d electrons. The separation in energy here represents the pairing energy of the electrons. So, for instance, the first electron in scandium will go right into a 4s orbital. The second electron goes in and has to pair up, so that slightly raises the energy. And then, of course, there's a pairing energy that is shown for the d orbitals, which is why we have two separate lines shown here. So, for instance, if you go down to the cobalt shown here, you can see, or let's say magnesium, you fill in 5 electrons into the lower level first, and then start adding electrons into the upper level, the upper line, because that represents electrons that are now being paired with the electrons that were originally added. You will also want to note the change in the energy relative due to the difference in slope for the 4s orbitals versus the 3d orbitals. So notice the slope is shallower for the 4s and much steeper for the 3d. So that actually the 3ds start to go lower in energy as you go across the series of transition elements. These diagrams are very nice for helping to determine the order of filling for the electrons in transition elements, especially in these anomalies, for instance, in chromium. You can see chromium has 1 electron in a 4s, and then starts filling in the 3D orbitals, and 5 electrons go there. This is a consequence, of course, of a balance between the fact that the d orbitals are lowering energy relative to the s orbital at chromium due to the Coulombic electron-electron repulsion energies and the increase in energy due to pairing. So we'll go over more examples of these in the group problems in class, but you have at least an introduction to use now to help you with understanding as you're reading the chapter to get ready for class.